All right, if you're an engineering student, you have definitely run into the bipolar junction transistor, the BJT. It is an absolute powerhouse in modern electronics, but let's be real, figuring out how to actually use it can be a little tricky. So today, we're going to pull back the curtain and tell the story of the BJT's three secret identities, its configurations. So here it is, the BJT. What a revolutionary little device. And its real power, its magic, comes from its connections. See, it's got three terminals, or legs: the base, the emitter, and the collector. Now, this simple three-legged design is what makes it so incredibly versatile, but it's also where a lot of us get tripped up at first. And that really is the million-dollar question, isn't it? You've got this component, you need to put a signal in, and you need to get a signal out. But with three possible connection points, where do you hook everything up? It feels like you've got this extra leg, and you're not quite sure what to do with it. Well, the brilliant solution to this puzzle is this idea of configuration. See, instead of there being just one right way to wire it up, the BJT is designed to be flexible. The way you choose to connect those three terminals can completely change what the transistor does. It's pretty cool. So let's get official for a second. What is a configuration? It's really just the specific way you connect the BJT in a circuit. And here's the key. You always pick one of the three terminals to be common. That just means it's connected to both the input side and the output side. And just like that, our extra leg problem is solved. The absolute best way to picture this is to think of the BJT not as just a screwdriver or a wrench, but as a multi-tool, kind of like a Swiss Army knife. It can be a current amplifier, it can be a voltage amplifier, it can be something else entirely. And it all depends on how you decide to hold it. Let's break that down with our multi-tool analogy. Step 1, you pick one terminal to be your common point. Think of this as the handle of your multi-tool. Step 2, you apply your input signal to one of the other two free terminals. And finally, step 3, you take your output from the last terminal that's left. It's really that straightforward. So, since we've got three terminals, base, emitter, and collector, that means there are exactly three ways we can set this up. Three fundamental configurations. It's time to meet the team. And they're named pretty logically, which is nice. Each configuration is just named after whichever terminal you make the common one. So you've got common base, common emitter, and common collector. Each one gives our little transistor a totally unique personality and a different set of skills. First up, we've got common base, or CB for short. And just like the name says, the base is our common handle. In this setup, we feed the input signal into the emitter, and we take our output from the collector. Next on the team is common emitter, or CE. This time, you guessed it. The emitter is the common terminal. Here, the input signal goes into the base, and we grab the output from the collector. And finally, rounding out the trio, we have common collector, or CC. The collector is now our common point. We put our input into the base, and we take the output from the emitter. So there you have it, three configurations, three totally different jobs for the very same component. Okay, so we have three different ways to wire up our BJT. But why? Why would we pick one over the other? Well, the answer is all about what each configuration is good at. It's about picking the right tool for the job. And in electronics, that job is very often about amplification, or what we call gain. We usually measure a configuration's performance with two key numbers. First is current gain, which is just how much the circuit boosts the current from input to output. And the second is voltage gain, which, you guessed it, tells us how much it boosts the voltage. Some configurations are great at one, some at the other, and one is great at both. Think of this table as the spec sheet for a multi-tool, and it shows some really interesting trade-offs. For instance, look at common base. Its current gain is actually less than 1. It doesn't amplify current at all. But then, look at common emitter and common collector. They can boost current by hundreds of times. Each setup has its own unique profile, its own strengths and weaknesses. So they all have their uses, for sure. Common base is awesome for high-frequency stuff. Common collector is a champ at something called impedance matching. But when you just want good old-fashioned all-purpose amplification, well, one of these configurations stands head and shoulders above the rest. It is the all-star of the team. And the all-star is the common emitter. So why is it the MVP? Well, our source materials says it perfectly. It's the only one that gives you a big boost in both voltage and current. And since power is just voltage times current, when you amplify both at the same time, the total power gain is absolutely massive. We're talking thousands of times bigger. And this chart says it all, doesn't it? While common base and common collector might get you a power gain in the hundreds, which is pretty good, common emitter just blows them out of the water. It's not even a close race. It's in a completely different league, which is exactly why it's the go-to configuration for building amplifiers. Just so that number really sinks in, look at that. Power amplification of over 1,000 times. That is the magic of the common emitter configuration. It's the workhorse, the MVP. It's really the reason transistors completely changed the world. So what's the number one thing to take away from all this? Simple. When you hear an engineer talking about using a BJT as a standard amplifier, 9 times out of 10, maybe even more, they're talking about using it in the common emitter configuration. It's the default, the most powerful tool in our BJT multi-tool kit. And that's the story of configurations. But amplification is only half the story. What happens when you stop using a transistor in its comfortable metal zone and instead you push it all the way to its absolute limits? Well, you get a completely different kind of job out of it. Join us next time as we explore the transistor's other secret identity, the digital switch.